Hello everyone, welcome to Alfonso Academy. My name is Peter Alfonso and we are into the second part of chapter Gravitation. So Nicolaus Copernicus was the scientist in 15th century. He said that Earth is not the center of the universe and probably the Sun is the center of the universe. So at that time in the 15th century and before that, it was believed that Earth is the main geocenter of the universe and everything else, the Sun, the Moon and all the other planets revolves around the Earth. Earth was considered to be the geocenter of the universe, and Nicolaus Copernicus spoke against. So at that time people were punished for speaking against. So Nicolaus Copernicus was thrown out of the kingdom for speaking against. You will even find people even in the 21st century that they are saying that Earth is the center of the universe and the Sun and the other heavenly bodies revolve around the Earth. But of course we all know it's not true. So at that time people were punished for speaking against. So Nicolaus Copernicus was thrown out of the kingdom. And then came the rich scientist Tycho Brahe in the 16th century. He spent all his life observing the sky, looking at the sky, studying the maps, mapping out the movement of the stars, the planets. And then he built a big observatory and he had many workers working out for him. And he had watchkeepers who were just writing down the maps, looking at the skies every night. So he prepared the most accurate map at that time. And then came Johannes Kepler, who joined Tycho Brahe, said let's work together. And after Johannes Kepler joined Tycho Brahe died. After a year he died. And all the matter, all the studies which Tycho Brahe had prepared were taken by Johannes Kepler. And he kept on studying. He believed what Nicolaus Copernicus had said, that Earth is not the center of the universe, and probably Nicolaus Copernicus also had added that probably the Sun is at the center of the universe. But of course we know that it's not true. And then came Michael Galileo, who invented telescope. With the invention of telescope, everything became easy. He studied the universe. He said that some heavenly objects are revolving around the Jupiter. Now that was a different story. People were saying that everything is revolving around the Earth, but Galileo discovered that there are objects which are revolving around the planet Jupiter. And because of that reason, for speaking against, even he was thrown out of the kingdom. Now Kepler kept his mind cool and he kept on studying. Johannes Kepler kept on studying and he proved that planet revolves in elliptical path, and that too they do not revolve around the Earth, they revolve around the Sun. And that led to the first postulate of Kepler's law, the first Kepler's law, which says that the orbit of a planet is an ellipse. The orbit of a planet. The planet revolves in an elliptical path with the Sun at one of the foci. The Sun is at the one of the foci. So first of all, ellipse is if you take a cone and take an inclined plane and cut that cone with the inclined plane, you will get a slice, and that upper open path is an ellipse. So he said that the planets revolve in an elliptical path with Sun at one of the foci, and that was the simple first law of Kepler. The second law says that the line joining the planet and the Sun sweeps equal areas in equal interval of time. Now, if this is the planet, this is the line joining the Sun and the planet. This is the line joining the Sun and the planet. The planet moves in the elliptical path. When the planet moves, when it moves from point A to point B, suppose if the planet takes 1 month to move from A to B, and then again the planet goes over here, it reaches to point C, and to move from point C to D, again it takes 1 month over here, and again it goes in a same elliptical path, and when it reaches to E, From E to F again it takes 1 month. So 1 month it takes over here, 1 month it takes here, 1 month it takes here. Now the Kepler's second law says that the line joining the planet and the sun sweeps equal areas in equal interval of time. Now we have considered equal interval of time 1 month, 1 month, 1 month. Now Kepler's second law says that it sweeps equal areas too in those equal interval of time. Now if you measure the area ASB, area of this ASB, area of ASB, it will be equal to area of CSD, area of CSD. These areas will be equal. This is what Kepler's second law says. If you consider the line joining the planet and the sun, and if you consider equal time intervals at any point wherever the planet reaches, then the measurement of the areas will be equal for that equal interval of time. This is the second law which was given by Kepler. And Kepler's third law says that the square of planet's period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. Now, first of all, we must understand what is planet's period. Period is what? The time period which is taken for one full revolution. One full revolution. Suppose the planet is over here at this instance. It will take full circle, full path, it will cover the full path and again reach over there. And whatever time it took to revolve that full path is called as time period, which is denoted by capital T, time period. Same way now the time period of our Earth is 365 days and a few hours. The fourth, of course, the fourth year is considered to be the leap year because of that. It is considered as 365 days is the time period of Earth. Earth takes 365 days to revolve around the sun. So that is the time period. And what is the mean distance now? Mean distance is denoted by small r. What is the mean distance? To get the mean distance, we have to consider 2 points where the planets are. Suppose the planet is at point A and after a certain period of time, planet reaches point B. So we have to measure this full A to B. We have to measure AB and then divide by 2. We'll get the mean distance of the planet from the sun. Now that is denoted by small r, and then we can go through this law. The square of the planet's period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. That means the square of the time period, which is t square, is directly proportional to the cube of the mean distance, which is small r. So t square proportional to r cube, and then we can remove the proportionality sign by giving it as a constant, a capital K, which you might consider as Kepler's constant. So t square will be equal to kr cube. So what will be k? T square by r cube. So k will be t square by r cube. Now Kepler had stated all these laws, he had studied all these laws, but he was not knowing why it is following, why the planets are following this elliptical path, why they are revolving around the sun. He was not knowing anything about it. He had observed, he had studied, and he had given these 3 Kepler's laws, but he was not knowing why these planets are obeying these laws. So these 3 Kepler's laws helped Sir Isaac Newton for his formulation of his theory of gravitation. Kepler was not knowing anything about gravitation. He had no idea about gravitation. He was not knowing why the planets are revolving around the sun. But these laws which he had formulated helped Sir Isaac Newton to study his theory of gravitation. And that led to something big, which is a universal law of gravitation. So Newton's universal law of gravitation states that every object in the universe attracts every other object in the universe with the force which is directly proportional to the product of the masses of those two objects and inversely proportional to the square of the distance between those two objects. So you can divide this law into three parts. The first part says that every object in the universe attracts every other object with a definite force. So this is the first part. Second part says that the force with which the objects attract each other is proportional to the masses of the two objects. For example, if you consider two objects with masses m1 and m2, and then see the force between them, then it is proportional to the product of the masses of the two objects, which is m1 into m2. So F is proportional to m1 into m2. This is the second part. And third part says that this force is inversely proportional to the square of the distance between them. So suppose if you consider this as the distance, which is d, then the force is inversely proportional to square of the distance between them. So F is proportional to 1 upon d square. D is the distance between the center of the two objects. So now it depends. Now for a spherical shaped objects, you can take the main center as the center of the sphere. But if the object is not a sphere, suppose it is having uneven shape, then it is taken as center of mass. Now what is center of mass? For example, if you take this duster, you cannot consider this as the center. Why? Because if you catch over here, it will fall down this side. Suppose if you catch right in the center middle, it might stay balanced, and that you can consider as the center of mass. Suppose even if the object is very much having like uneven shape, and this side it is too big and this side it is too long, too small, then center will be where its mass is concentrated, where its maximum mass is concentrated, and it can stay balanced. So that was considered as the center of mass, and the distance was measured from the center of mass from the two objects, and that was considered to be d. So by combining these two equations, we are getting as F is proportional to m1 m2 divided by d square, which is the product of the masses of the two objects and square of the distance between them. So to remove this proportionality sign, we have something called as universal gravitational constant. It is denoted by capital G. We'll come back to the capital G, universal gravitational constant, little later. So this is what Newton's universal gravitational law says. Every object in the universe attracts every other object with a force which is directly proportional to the product of the masses of the two objects and inversely proportional to the square of the distance between the two objects. So now if you remember the formula, you will remember the definition. If you remember the definition, then it is easy to derive the formula. So from the formula you can get the definition, and from the definition you can always remember the formula. So it is necessary to study either of the things. Now how to get the definition from the formula? See, F is proportional to m1 m2 divided by d square, which says that there are two objects. Between them there is a force which is directly proportional to the product of the masses of the two objects, and it is inversely proportional to the square of the distance between them. Now take for example this distance which is between the two objects is 1 unit, it is 1 meter, and the masses of the two objects are also unit kg. Suppose 1 kg, both the masses. Then this value m1 m2 divided by d square will be 1, and at that time F will be equal to G. So the gravitational force between the two objects will be equal to the universal gravitational constant or universal constant of gravitation. So now next, if we take the masses to be 2 kg, 2 kg and the distance between the object as 2 meter, what value we will get for F? Let's see. So G and M1 is 2 kg, M2 is 2 kg and D is 2 meter square. So 2 square. So what you will get answer for this F? 2 into 2 is 4, 2 square is also 4, 4 cancels, F is equal to G if masses are same, which is 2 kg and 2 kg. Now consider first mass M1 becomes double. So F will be G into 2 kg becomes 4 kg. So it will be 4, then mass 2 and 2 square. So this will be 8 divided by 4, which is of course 2. So F will be 2 times G. 2 times G. So we have seen that if suppose M1 is double, then automatically the force also gets double. F was equal to G, but here it becomes 2G. The force gets double if one of the masses gets double. Now consider what will happen if suppose the distance between the two objects is double. So instead of 2 meter it becomes suppose 4 meter. Let's check it what happens to the force. So G into first object is 2 kg, second object 2 kg and the distance becomes double. It becomes 4. So D square, 4 square. So it will be 2 into 2 is 4. 4 divided by 4 square, which will be 16. So 4 divided by 16, it is 1 upon 4. So 1 upon 4 times G. So F becomes 1 upon 4 times G. So if suppose distance between the two objects is double, then the gravitational force between the two objects is gets decreased by a factor of 4. It gets decreased by a factor of 4. So of course I have not taken the units in these cases. It is unit for force is Newton. Now capital G is the universal gravitational constant. Now in order to get the units for this capital G, we have to learn the formula well, which is a formula for gravitational force. F is equal to capital G M1 into M2 divided by D square, where M1 and M2 are the masses of the two objects. Of course, where there is a gravitational force between them. Then D is the distance between these two objects. And then substitute the units for the remaining quantities and then get the unit for this capital G. So we'll do it here. Gravitational force, the unit is Newton. M1 into M2, these are the masses. So kg into kg is kg square. And D is the distance, so it is SI unit is meter, so it will be meter square. Now keep G on one side, rest of the quantities you take on the other side. You will get the unit for this capital G. So G will remain the same side. This meter square will go in the numerator on the other side, and then this kg square will come in the denominator. So this is nothing but the unit for this capital G, Newton meter square per kg square. So you can write it in a better way, Newton meter square per kg square. So these are the units for universal gravitational constant. Now you can see that I have taken this kg into the numerator, so its power changes the sign. So this positive 2 becomes negative 2. So it is read as Newton meter square per kg square. Now for this universal gravitational constant, a specific value was given. It was experimentally founded out by scientist Henry Cavendish. It was given as 6.673 into 10 raised to minus 11 Newton meter square per kg square. So this was the value given for this universal gravitational constant. Now we have to remember these values well, this formula very well, because you will come across almost in many of the problems as the chapter goes on. So this is rounded off to as 6.67 into 10 raised to minus 11 Newton meter square per kg square. This was the second part of chapter gravitation. Next part will be finding out the magnitude of centripetal force, and we'll see what is Newton's inverse square law of gravitation, and we'll be solving some numericals. So hope you have understood whatever I have taught you in this part, the second part of chapter gravitation. And if you don't understand something, then please leave a comment in the comment box. I'll be definitely replying all your comments. So thank you very much for watching this video. It's Alfonso Academy. Please share, like and subscribe my channel. Thank you very much.